All right, welcome. This is Ryan Hoger with Temperature Equipment Corporation, and this week's webinar, actually this week and next week's webinar, are ABCs of comfort. I assume when you all registered, you saw that it was a two-part series, so an hour and a half today and an hour and a half on next Monday. For those of you that are interested in PDH credits and registered as a PE, you do need to attend both sessions to get the credits, and there's also going to be quiz questions on both days that you need to answer and answer correctly in order to get credit. All right, so with that, we're gonna go ahead and start things off. So our topic is ABCs of comfort. This is meant to be an entry-level topic or a refresher for some of you, just to kind of remember how things work in terms of human comfort and what we can do from an HVAC perspective to help aid that along. So this is kind of our agenda for this week and next week. We'll talk about comfort, we'll talk about requirements of the system to generate comfort, we'll talk about heat transfer, talk about air conditioning systems specifically, different types, furnaces, boilers, electric heat. We'll talk about the refrigeration cycle, and we'll kind of try to tie all these things together as well. So just for starters, we're going to stick in the purpose of this class to HVAC for comfort applications. We're not going to talk about anything that's process related. Comfort means we're doing it for the purpose of cooling, heating, dehumidifying, people-based sources. Process would be, manufacturing and things like that. So we're going to stick with the people side of things for this class. The equipment is going to be very similar, but what we're using it for is going to be different. And you can tell some of my slides are a little bit dated based on the computer monitor and or the hairstyle. But we're going to stick with the people-based loads, and we use mostly commercial examples today, even though the same principles are going to apply residentially. So starting us off on the comfort side of the equation, the comfort really depends on what people are using the spaces for and what they're doing. So there are several different ways that we are going to be measuring the comfort level of people and different parameters that are involved. And if we just focus on the main one, which is dry bulb temperature, and we skip some of the other ones, you're really going to end up with unhappy occupants, even though the thermostat will say it's the exact temperature you asked for. Because you have to understand that temperature is only one piece of the comfort pie. And only one piece of the thermal comfort pie for that matter. So most of you are probably already thinking about humidity as well. Humidity is a big influence on your comfort. If things are too dry or things are too moist, it's going to lead to uncomfortable situations. Additionally, as we talk today and next week, you'll see that temperature and humidity are not exclusive of one another. If I have higher temperatures, I can tolerate lower humidities and vice versa and stuff like that. So they do influence each other in terms of comfort, and we'll talk about how that relates. The next one is air motion. So not only do you need to have appropriate temperatures and humidities in the occupied space, but you may have to have more or less airflow to make people comfortable. So depending on whether they're cold or hot, right? So when I was a kid, I'd come in from outside. I didn't have air conditioning growing up, but I'd come in from outside. I was all hot and sweaty. The first place I would go stand was in front of the fan, in front of a box fan. The temperature on the inlet side of the fan and the outlet side of the fan was not any cooler. In fact, it was probably slightly warmer because there was some waste heat from the motor. But to me, it felt way cooler than if I was just standing there with no airflow, right? That airflow comes across your body and takes the heat and removes it from your body and puts it somewhere else behind your body, right? So that airflow can help cool you off. Likewise, if someone's already cool and cold and there's too much air motion, they'll complain about drafts and stuff like that. So having the appropriate amount of air motion in the space to either blow directly on occupants or not does have an effect. Additionally, in many types of systems like overhead heating and cooling systems in an office building, we need to have the air motion in order to get the air changes in the room. We also have radiant temperature. All right, so radiant temperature is quite a bit different than dry bulb temperature. Dry bulb temperature is just what's the straight up temperature in this room. I take an old mercury thermometer, I stick it in the room, what's temperature say? Right? There's also wet bulb temperature, which we mentioned earlier in terms of relative humidity, and we'll kind of talk about how they're interrelated. Wet bulb temperature means I take a thermometer, I basically stick it inside a wet sock, and then I take the temperature reading. And usually the wet bulb situation is going to be cooler than the dry bulb situation. I got that evaporative effect, and we'll talk about how that works in a little bit today. The radiant temperature is yet a third temperature in a space that will influence your comfort, and it's not directly related to the dry bulb temperature. I mean, the radiant temperature will change the dry bulb temperature, but it's not the same thing. So by that, let's take an example. If I walked out, well, today it's a gloomy, nasty day, but if it was a sunny day outside and I walked outside and my thermometer said it was 60 degrees out and it was sunny, I would feel kind of warm, right? But if I walk out today and it's 60 degrees out and cloudy, I'm going to feel cool. It's going to feel different today than it would on a sunny day. That sun shining down on your body, that's radiant energy. That radiant energy is that temperature difference in the radiant side is warming up your body or any object for that matter. So radiant temperature is a directional heat. It is directly shining at something. We can measure the surface temperature of whatever has been under the radiant heating exposure and see what that temperature is. And it will be often different than the dry bulb temperature in that same given room. Not on the thermal side of the equation, but just in comfort in general, air cleanliness has an effect. If the air is dirty and there's pollen in the air or there's dust in the space, people tend to find that to be uncomfortable in terms of either A, perception, or B, allergies and stuff like that. So it doesn't have any effect on your thermal comfort, but does have an effect on your overall comfort, if you will. And same thing with other stuff going on in the space. Odors, right? If I took exhaust air from your bathroom and I ducted it into the supply air of your office, you probably wouldn't be very happy with that. That odor would not be very pleasant. It would make you uncomfortable. Thermally, you'd be the same, right? But comfort-wise, from an odor perspective, it would not be pleasant. And then sound as well has an effect on comfort, as does lighting, which I don't have on the slide here. But those things do affect your comfort, just not thermally. So the first four are main thermal drivers: dry bulb temperature, relative humidity / wet bulb temperature, air motion, and radiant temperature. Those are the big four. So there's different stuff we can do with an air conditioning system in order to affect those temperatures and parameters in order to make people feel comfortable. Obviously, we can heat the air. Obviously, we can cool the air. Everybody always thinks of that. But we can additionally humidify the air, which means we add moisture to it to improve the relative humidity and or wet bulb. We can dehumidify the air, which means we take moisture out of it if things are too moist in the space. We can bring ventilation air in to help with the air cleanliness and odor perception type stuff. We can filter it, which also helps out with the air cleanliness. And we got to circulate air around the space to get these effects to happen in not just one space, but throughout the whole room, if you will. So we need to circulate the air. All right, so let's do our first quiz question to make sure everybody has this under control and knows how to do the questions. So I'm going to put it up on the screen here. Let me grab the question box. I'm going to put the questions up on the screen. I'm going to read them to you, and then I'm going to open up the questions. I'm going to read them first because I found that sometimes people start clicking on the answer and they don't really read the question first. So I'm going to do it the old school way. I'm going to read it to you, right? So first question, the main human thermal comfort parameters include A, dry bulb temperature, humidity, daylighting, air motion. B, dry bulb temperature, humidity, air motion, radiant temp. C, wet bulb temp, humidity, acoustics, odor perception. D, temperature, humidity, daylighting, air motion, and acoustics. All right, so you're going to pick one of these answers that defines the main human thermal comfort parameters. And while you guys are filling that out, you should know that on the bottom right-hand corner of your portal, there's a chat question box area there. If you have a question on something as we're going through it today, type it in that question chat box. And when I'm giving you guys the poll questions, I'm going to glance over at those questions you type in for me, and I'll try to answer as many of them as possible while we're still on the air. And if not, I'll get back to you later if I can't get to all of them at the time. So it looks like 70% of people voted. We'll give it a few more seconds here. Remember, if you are doing this for PDHs, for professional engineers, you do have to answer the questions. So I'll close the poll in 5, 4, 3, 2. I'll put the results up here. The vast majority of people got it right. 87% of you said B, which is that the main thermal comfort parameters are dry bulb temperature, humidity, air motion, and radiant temperature. That's not to say that daylighting and acoustics and odor are not important things for your comfort. They're just not thermal related things. All right. So let's go back to our slides here. So we got to be able to figure out where the heat comes from in a building and how we're going to get rid of the heat, or if we don't have enough heat, how we're going to add the heat. But we got to know all the sources of what we have available to us to begin with. So the first thing is that people are a giant heat source in a lot of buildings. In commercial buildings, considering that the density of people in most commercial buildings is much higher than the density in a residential building, right? You got someone in a cubicle every 10 feet versus your house, you got 2,000 square feet for like 3 people. People are a big load in the building, right? So the rate of heat that people generate depends on their activity level, right? So in this case, the guy on the left is sitting in a chair, minimal activity level, hence minimum heat generation. The lady on the right is, I don't know what she's doing. She's either dancing or she's doing some kind of fitness thing or whatever. So she's obviously generating a lot more heat than he is. Your activity level specifically dictates how much heat your body is going to generate. The more heat your body generates, in many cases, the more heat we have to remove from the space. Or if it's heating scenario, less heat we have to add. So we need to understand how people generate heat based on what they're doing. There are 4 ways that your body gets rid of heat. And make no mistake, in most scenarios, especially indoor environments, your body is always trying to get rid of heat. Even when it's cold out and it's a 0 degree day outside and it's 68 degrees in your office or your house, your body's still trying to get rid of heat. Now, it's not trying to get rid of heat as much as it does on an 85 degree day or an 85 degree space, but still trying to get rid of some heat. So usually we're trying to get rid of the heat. Your internal body temperature, as you know, is 98 degrees. Your skin surface temperature is cooler than that. It's typically, 92, 93, 94 degrees skin surface temperature. But in most cases, the surrounding air around you is cooler than your body, and your body is giving heat to that surrounding air. So there are 4 main ways that we get rid of heat from our body. And we'll go through each one of these in detail because they are going to have an effect, because these are the same processes we're going to use in HVAC equipment. There's conduction, convection, radiation, and evaporation. And we'll talk about all 4 of those and give examples of each so you can kind of see what your body's doing in those regards. So the first one is conduction. Conduction is basically direct contact with the heat source. They're showing here that someone's got their hand on a metal bar, right? If you're holding that metal bar, it's eventually going to get hot in your hand and you're going to feel that. If you walked into your kitchen and you had an electric stove and you put your hand right down on top of the electric stove and touched it, direct transfer of heat would go from the electric coil into your hand, right? Obviously, don't do that. That would be stupid. But that's how that would basically work. So conduction is directly touching the heat source. So in terms of people, it's typically your hand or your arm or your leg or whatever having direct contact. In normal operation with your body in the commercial building, you're walking around the floor. There's conduction between the floor and your feet. There's conduction between your desk chair and your butt. There's conduction between your desk and your elbows where your arms are resting, right? So all these different things you're touching are directly transferring heat. In HVAC equipment, we're going to do the same thing. We're going to have things touching other things and transferring heat that way, right? It could be a flame touching a heat exchanger or something like that. And we'll talk about some of those things as we go. Air temperature does have an influence on conduction. Not only is there conduction between your body and objects, there's conduction between your body and the air that's right next to your body. So just imagine you're standing there and there's this, we'll just say there's this 1/2 inch wide layer around your body, right, of air, and that air is being in direct contact with your skin and your body, and there's conduction between your body and that air. The way that conduction works, in fact, the way that heat transfer in general works, is heat always goes from the hot thing to the cold thing, right? So whatever the hotter source is, it's going to move from that to the colder thing. It wants everything to be in equilibrium with each other. And basically become the same temperature eventually. That's the way heat works. So it goes from hot to cold. The speed at which it goes from the hot thing to the cold thing has to do with the temperature difference between the two. If my body is 92 degrees surface temperature and the air around me is 91 degrees, I'm not going to give heat to the air very quickly at all, right? But if my body's 92 surface temperature and I'm standing outside and it's 0 degrees, I'm going to give heat up really quick to the outdoor air. Very fast. So the speed at which my body gives up the heat, it has to do with the delta T between my body and the air right next to me. The same thing's going to happen with any conductive process. The speed at which the heat's going to transfer is going to be based on the temperature difference between the two objects. Our object right now just happens to be a person that we're talking about. Right, so in this case, the body's 92, so the closer I am to 50, that's a 42 degree temperature difference. I give the heat up pretty quick. my 92-degree body in an 80-degree room does not give the heat up very quickly at all. Clothing has an effect on our ability for conduction. Clothing is an insulation form, right? So insulation slows down conduction. If I were to take back to that, that metal rod with the candle deal, if I was to put a glove on, it wouldn't burn my hand quite as much. If I had a pot holder on my hand, it wouldn't burn my hand quite as much. I wouldn't feel the heat as early. I could probably stand there for 20 minutes with the pot holder in my hand holding the iron bar. But without the pot holder, it's probably only going to be, a minute until it gets really hot. So there are things that insulate for conduction. And in terms of people, that's typically our clothing. So your clothing level, how much clothing you have, has a big influence on your comfort. Now, from the HVAC perspective, it's not too often we get to dictate to people in a building we're designing or operating or servicing what clothing level they're going to be wearing. They're pretty much going to do whatever the heck they want, and we're going to kind of be stuck with it. So we got to just kind of plan for the best. Chances are the dude with the swimsuit on the left side is not coming into the office like that, right? On the flip side, if this is a YMCA pool, the chance of the guy coming in with a suit is pretty low also. All right, so the clothing level is typically dictated by the usage of the space. And from a design standpoint, we're going to take our best guessage at the clothing people might be wearing based on the usage of the space. But the clothing will slow down the rate of conduction between the human occupant and the air itself. So our next form of heat transfer, and by the way, if you guys have any questions, type them in the chat box there and we'll try to get them all answered. Our next form of heat transfer is convection. We're mainly concerned with convection in air, but one of the examples we have here on the screen is convection in water, just to kind of illustrate it. So in this case, I took a pot of water, I stuck it on top of the stove. The flames down there in the bottom, licking the bottom of the pot, that's being transferred from the flame to the pot, mostly with conduction, directly touching the bottom of the pot. But once I start heating up the bottom metal of the pot, that pot heats up the water, which is also conduction. But then once I heat the bottom layer of water, that bottom layer of water, those water molecules on the bottom, they're warmer than the ones on top. And you probably already know that, hot air rises. Well, hot water rises too. That's why if you go swimming in a pool and you dive to the bottom of a 12-foot pool, it's cooler down at the bottom than it is at the surface. Same with a lake or whatever. Same in the pot of the water. The cold water drops to the bottom, the hot water rises up. The density of water is heavier when it's cold, so it sinks. And then hence the buoyancy of the warm water pushes it up to the top. So when I heat the bottom of that pot and it starts to warm up that water, all that water is going to move up. And you can see the arrows here. The warm water is going to move up and the cool water is going to move down. And I'm going to get this circular pattern going on in these pots. The water rising and falling, and basically trying to come to an equilibrium state. The same thing's going to happen with your body in the space. Not only is there conduction, that is your body transferring heat to the air by directly touching the air with your body, then there's going to be convection, which basically is going to be similar to that pot of water where the air that's warmer is going to want to rise up. So as your body uses conduction to heat the air, convection then kicks in, and that warmed up air then rises up, right? So if I were to take my little cheesy spotlighter thing here, right? Let's just say there's my foot warms up this one little air molecule on the bottom right over here. That air molecule rises up the side of this guy's body and moves away. But when he moves up, there's a space there that has nothing in it. So then a new air molecule comes in and takes his space, and he gets warmed up and moves up. And then a new one comes in and moves up. So there's basically an air motion pattern around your body with no fans or no breezes or no nothing going on, just a natural process that's happening of the warm air rising and going up your body and new air coming in and then rising and going up. That loop basically happens. So if I was just to stand here and do nothing, I'd have this loop of air transfer going like this. The warm air would go up, the cool air would fall, and it would all be based on my body being the heat source. It's very similar for you guys that have been in apartment buildings or whatever, or houses that have baseboard electric heat or baseboard hydronic heat sources. There's no fans in those baseboard heaters. Basically, the coil just gets heated up by the electric or water that you're providing to it. And when it heats up, that air rises up out of the baseboard and new air comes in the bottom. By the way, that's the same reason that you don't stick boxes in front of the baseboard and stuff like that. It doesn't heat very well if you block the cool air from coming into the bottom of it. So you need to have that space open to draw that cool air in so it can get warmed up by the coils. So that's a natural process, convection, warm air rises. You probably already knew warm air rises, right? We can also aid that process and not do it all naturally. We can use fans to force the air as well. So this is showing you an example of a supply duct in space where I can blow air into the space and using diffusers and force the air motion to happen. Forcing the air motion to happen speeds the whole process up. If I just waited for this to happen, there'd be a lot of people that are probably hot, and I have to keep the space really, really cold for them to be comfortable. I have to keep it, let's just say for sake of argument, like 65 degrees in the space if I had no air motion, and you'd be comfortable. With air motion, I'll keep it in the low 70s, and you'll be perfectly fine. So we're going to force that air around to generate the motion mechanically to speed up the process so I don't need to have as cool of a temperature. Kind of like that example I said before where you might stand in front of a fan and let the air blow heat across your body. Same kind of idea here. Our third type of heat transfer is radiation. So I gave an example earlier with going out on a sunny day when it's 60 degrees. If it's sunny, it feels warm. If it's cloudy, it feels cool. It's the exact same 60 degrees outside. It just feels different because the radiant energy the sun is shining onto your body. Here's another example of that. This guy is sitting here by the campfire. It's 50 degrees outside, right? So that's the temperature of the air all around him. But that fire has infrared heat associated with it. And that infrared heat is directional, just like the sunshine. If you go under a tree, you don't feel the sun heat. You step out in the open and you feel the sun heat. Same thing with the campfire. It's directional heat. So that radiant heat leaves the campfire and shines directly on this guy's body. So his entire front side of his body is going to get warmed up by that campfire. But his backside is still going to be 50 degrees freezing cold. It's directional heat, right? And it's infrared. It's invisible. You cannot see it. It's invisible radiation waves that are traveling from that fire to whatever object it hits. So in this case, the guy, the wood logs, the grassy patch, whatever. It's shining directly on him. So if he was to put a tarp in front of him and the fire, he would not feel the heat as much. The tarp would block it. There's radiation sources in buildings, right? We can have radiant heating and radiant cooling for starters, and we mechanically do stuff. But unrelated to that, in a normal building, regular surfaces in the building are going to generate radiant heat as well. So just like with the other forms of heat, the energy always goes from the hot object to the cold object, right? So in this case, this guy, his body is 92 degrees, 94 degrees surface temperature, whatever it is. That window surface, let's just say it's a double pane window and it's minus 10 outside. So the inside surface of that glass is like 46, 47, 48 degrees, something like that. So his 47 degree window and his 92 degree body, heat's going to go from the guy to the window. So infrared heat is going to leave his body and shine to the window. So when he's walking past that window, he might say, ooh, it's cold. I can feel the coldness coming off of that window. Well, the coldness is not coming off the window. The heat is coming off of his body. His body is giving its heat up to the window. He's literally heating the window with his body heat with infrared energy, right? Same thing happens in the opposite scenario. If it's really hot outside, and really hot means that the glass surface temperature in this case is warmer than his body, right? So let's say it's a 100-degree day out. So the inside surface of my glass is like 95 degrees or something like that. So that 95-degree glass is shining infrared heat to my body because my body is only 92, 93 surface temperature, right? So the higher temperature object shines infrared invisible heat to the cooler object, right? In most spaces, it's the human that's the hotter object in an indoor space, but there are scenarios where that's not the case and the object is warmer. The same thing happens when you come into your office building in the morning, in the winter time or even the spring and fall time, and you sit down at your desk, and even though the thermostat in your office says it's, whatever you asked for, 70 degrees heated, and it's 70 degrees, perfect temperature, you got everything you asked for, you sit down at your desk, and you're like, ooh, this desk is chilly, right? The surface temperature of the desk is not 72 yet. We just turned the heat on half an hour ago. We heated up the air to 72. It takes a long time for that air to now turn around and heat up the objects. So your desk is still 60, 65 degrees, so it feels cool when you set your arms down on it. All right, even though the thermostat says everything's great, because it's great. It is great at the thermostat. It's just not great at the surface temperatures. But then your body will be using radiation and conduction to interact with the desk and the floor and those sorts of things. All right, so it always goes from hot to cold thing. It's the invisible infrared waves. So some typical surface temperatures that you might have regarding the structure of your building. Here's a residential chart. I'll show you a commercial chart in a second, just for example's sake. But here's where I was saying, down at the very bottom one down there, was the example I had just given a second ago. If it's minus 10 degrees outside in the wintertime and I have a single pane piece of glass, my inside surface of my window is only positive 10 degrees. That piece of glass is only helping me basically 20 degree delta T. So my 10 degree surface temperature, when I walk past that window, it's going to feel really cold. If I got double pane glass or single pane glass with a storm window like they're showing here, on a minus 10 degree day outside, my inside surface temperature of the glass is 47. It's a big difference in terms of that window's ability to reduce the amount of radiant heat transfer from my body to the glass because it keeps the glass surface warmer. Other things in the space, doors, windows, walls, roofs, they have a much better insulation value, much better R value, if you will, and that reduces the heat transfer. So my wall with R11 insulation, which is pretty low end these days, on a minus 10 degree day, my wall is 69, right? So that insulation is saving me a 79 degree delta T. Well, with a 69 degree wall, my body doesn't give up nearly as much heat to the wall as it did to the single or double pane piece of glass. Right. And the same thing happens in the winter. In this example, they're showing 95 degree days, 95 degree day with a 75 degree inside temperature. You can see that window is basically 90 degrees, which is pretty warm. So it's hard for my body to give up heat to some of these objects when they get closer to my body temperature. If anybody has any questions, type them in the chat box and I'll help try to answer them. So far, no questions. Commercial, it's a very similar scenario. The window construction and wall construction expectations are a little bit different commercially, but it's the same basic principle idea. The better the window, the better the doors, the better insulated values, R values and U values of those objects, the more it's going to slow down the transfer of heat. Our fourth type of heat transfer is evaporation, right? Or in terms of people, you can call it perspiration or sweating. So each pound of water can absorb about 1,000 BTUs of energy. The ability to transfer heat via evaporation is absolutely key. It is, arguably, if you're a Darwin fan, one of the things that help people evolve faster than other animals. That and our thumbs probably are the two big ones. Thumbs, the ability to sweat, and brain size, right? Those are what makes humans different from all the other animals. Literally, people lived in very hot climates back, tens of thousands of years ago, and their main mechanism of hunting was to chase animals until they died. The animals could not give the heat up as fast. Animals cannot run people for short distances typically, but when we start running for, 10, 15, 20 miles, most animals can't give up the heat. They overheat and they'll fall down and die if you just keep following them. So it's kind of a weird example, but your body gives up quite a bit of heat via sweating. It's a main mechanism for your body to give up heat. It's not the everyday thing, right? It's not the main one, but when you start getting really, really warm, that kicks in very quickly because it can give up the most BTUs as rapidly as possible. So basically what happens, your body sweats and now you have moisture on your skin. And your skin, the moisture on your skin changes state. It basically boils off and evaporates, right? The way it does that is it needs heat in order for that moisture to evaporate. Well, where does the water on your skin get the heat from? It gets it from your body. It pulls the heat from your body, basically boils it off into steam, if you will, if you want to think of it like that, and evaporates it away. So it's a big energy requirement in order to change the state of any fluid. So to change it from a water into a water vapor, we need a lot of energy. We take that energy from the heat of your body. So it's very effective at moving energy that way. We do use evaporation in HVAC processes. The biggest example of that is probably a cooling tower, where we have a chiller system and we send 95 degree water to the cooling tower, and we mist it out into the air and use fans to run the air across the mist and let it evaporate out the heat, and basically whatever condensate is left, we return it as 85 degree water. We cool it down 10 degrees with just evaporation. In some markets, they'll also use evaporative cooling equipment in lieu of mechanical refrigeration compressors. So like in Arizona and stuff like that, you might hear of like swamp coolers and things like that, where we can use moisture to control the energy transfer rates. But this is a big one for your body to be able to get rid of heat through evaporation. But evaporation by itself doesn't work so great. Using it in conjunction with convection, right, that was the air motion heat transfer, using them together is where the real big payoff comes off. So if I can keep the air moving around your body, it can evaporate away faster. So if the air is not moving, the moisture will tend to just kind of like roll down my arms and drip off onto the floor, which is kind of gross. But if I can keep the air moving, for example, I'm standing in front of a fan while I'm sweating, it takes that heat away really quickly. Right, so when you ran inside the house as a kid, all sweaty, and you stood in front of that box fan, it felt awesome because the box fan was moving that air away from you, and it was helping that evaporation process go along. So the more air motion that you have, the faster the evaporation rate is going to be. Eli types in, I don't know if it's a question or it's a statement, he types in air temp is maintained by the humidity. It is the heat energy in the moisture that determines the length of time for transfer. Not quite sure what you're asking or stating there, Eli. Air temperature and humidity are interrelated, and the total heat energy available in the air is a combination of the sensible heat, which is the temperature-based heat, and the latent heat, which is the moisture-based heat. So two of those things add together to determine the total content of heat that is there. So I'm not sure which comment you were referring to on there, but you could type it in further and we could try to answer it more if needed. Oh, okay, he typed in a comment saying it influences the heat transfer. That is correct. The temperature and moisture contents, as well as the air motion, are all going to be interrelated to each other. All right, so air motion increases our rate of evaporation. All right, let's go to our next quiz question here. Let's pop that guy up. All right, which of the following methods of heat transfer is not used by our bodies to maintain comfort? So which of the following is not, N-O-T, right? So pick the bad one here. So the choices are convection, evaporation, insulation, conduction, and radiation. Right? So four of those are main heat transfer mechanisms that our body's going to use. One of them is not. Pick the one that is not. Looks like about 82% of the people voted. So I'll give it another 5 seconds to wrap up here if you haven't already answered. All right, and then I'm going to go ahead and close the quiz and share the results with you guys. 81% of you got it correct. Insulation is not a method of heat transfer. Insulation is a blocker of heat transfer, if you will. It reduces the heat transfer. The main mechanisms to transfer the heat are convection, which is the direct touching, evaporation, which is the sweating, the moisture-related one. Convection is the air motion. Evaporation is the moisture-based one. Conduction is directly touching, and radiation is the infrared. Insulation is not a heat transfer mechanism. It's a stopper of heat transfer, if you will. All right. Let's go back to our slides. All right, so let's talk a little bit more about moisture in the air. So we use this term relative humidity a lot, and you'll see it on HVAC documents. It's listed as %RH. RH stands for relative humidity. It's called relative humidity because it's relative to something versus absolute humidity. So this is kind of how it works. So we basically add up all the water molecules in a given volume of air. And then we look and see for that temperature air, how many water molecules could we possibly hold before we were fully and completely saturated, right? That percentage is our relative humidity, right? So I'll give you a couple examples of that. Did I just go backwards? Oh no, there we go. Sorry. All right. So we got this pound of air we yank out of this room, right? So we got this little box, we yank up a pound of air out of it, we get out our little magnifying glass, right? And we count up every single grain of moisture in there. A grain of moisture is a unit of moisture. For conceptual purposes, if you want to think of it, just think of it as a little one drop of water, right? It's not exactly that, but just kind of think of it that way. So I got 55 little grains of moisture. I counted them all up in this box, right? That's what I'm starting out with in this case for this particular air at 70-degree temperature. Now, a lot of you guys have probably seen a Psych Chart, and Psych Chart is a whole separate, 3-hour class in itself. But I'm going to give you kind of the quickie version of how this guy, the Psych Chart works. And this is a simplified version of the chart with a lot of the parameters removed and just the ones we need for today's discussion. So down the bottom axis, we have dry bulb temperature. And in this case, the chart goes from 30 to basically 115, 120 degrees on the chart. Up the vertical axis, we have the moisture content, and it goes from 0 to 180 grains of moisture on this particular chart. That's all my actual water moisture. So it's my specific humidity, my actual humidity. I'm adding up all those moisture droplets. On this chart, there'll be curves eventually as we talk further with humidity percent on them. This one curve here along the top side, that's my 100% relative humidity curve. There's no chart to the left of that, because the left of that, my air would be fully saturated, and I'm not going to be adding any more moisture to that air. So the chart just doesn't exist on that side for psychrometric purposes, for air purposes. So once I get to that line, I cannot continue to add moisture to it. I realize there are things such as supersaturation, but for HVAC, that's not part of our realm. So we're just going to stick with that side of the chart not existing. So my regular room air temperature, right? We said our room was what? Oops. We said our room was 70 degrees, right? So I take my 70-degree room air, maybe. Oops, there we go. And I go straight up the chart, right? 70 degrees straight up the chart. I hit the 100% saturated line, meaning I cannot hold any more moisture if I wanted to. And then I follow that line all the way across, and that tells me 110 grains of moisture. So at 70-degree temperature in a room, the most moisture it could possibly hold is 110 grains of moisture, and that means it's 100% humidity in there, right? So that's how much it could possibly hold. And I said I had 55 grains that I measured when I counted my box here. All right, so I measured 55. It could possibly hold 110. So my relative humidity in that case is 50% humidity. I got half of the maximum. The maximum is 110. I got 55. All right, so that's how the relative humidity math works, if you will. How much could I possibly hold at this given temperature? How much do I actually have? I'm 50% saturated. Right? Relative humidity tells you what percent saturated you are. Warmer air can hold more moisture, right? So I go back to that Psych chart, and I'll bring my little bubble back up here. 70-degree air, I could hold 110, but if I had 80-degree air, I went up the chart here, I could hold 155 or something, or whatever that was. If I had colder air, I had only 50-degree air, then I can hold like 57 grains of moisture. So the warmer the air is, the more moisture it can hold, right? So that's going to change my relative humidity. Let's do that example then, right? So now I got the same 55 grains of moisture content, but instead of 70-degree air, I have 92-degree air. So when I go back and look at that chart, instead of holding 110 grains of moisture, I can look at the Psych chart and see that 92-degree air will hold 220 grains of moisture. So for you guys that are math whizzes, I have 55, the max is 220, I am 25% saturated, right? I have the exact same amount of water as I did in the other example, but now I'm 25% humidity instead of 50% humidity because I changed the temperature of the air so it can hold more, right? So this interrelationship between the temperature and the amount of moisture content it can hold is directly going to affect our comfort. Remember we said humidity was part of the discussion? This is why it affects the human comfort. Do one more example here. So this is somebody's building, their house, whatever it is. They have it currently at 70 degrees in the space, and there's 7.5 grains of moisture for every pound of air, and that comes out to be 7% relative humidity. It's a fairly dry situation. I have infiltration coming into this house or this building. Air leaking into my building is infiltration, and it's fairly cool outside on this given day, 20 degrees outside. The moisture content is exactly the same in this particular scenario. It's 7.5 grains of moisture per pound, right? So the inside and outside moisture is identical, but outside it's 7.5 grains on a 20-degree day. So it's 50% relative humidity outside because that air cannot hold as much moisture, right? So that air leaks into my space, and that air becomes a much drier feeling air because I can hold more at 70 degrees than I can at 20 degrees. So it starts out at 50%, 7.5 grains. It leaks into my heated structure, and my moisture content is still the same in this case. My relative humidity percent drops because I heat the air up. In some of these kinds of cases, if you have dry air like that in your house or your building, you may need to add humidity to it with a humidifier. It doesn't happen a lot residentially because there's so many people occupants in the building that generate moisture as well. But if it's certain types of spaces where I have electronics or wood products or things like that, then I typically need to do it more. The looser my building is and the more outside air I leak in, the more likely I am to need a humidifier as well. The ability for your body to remove heat via evaporation depends on the humidity around your body. If the air around your body is really dry, it is very easy for me to use evaporation to sweat my heat to the air, if you will. If it's really humid, it's very hard for me to do that. So an example of that might be if I go outside in Las Vegas when it's 90 degrees outside, and it's super dry in Vegas, right? So it's 90 degrees and super dry out there, and I sweat. I don't even see sweat in my body typically in Vegas. It just evaporates off immediately. It gets taken away before I can even visually see it, right? And it doesn't feel too bad when it's 90 degrees in Vegas. But then if I go to Miami, where it's known to be a very humid place, and it's 90 degrees in Miami, same exact air temperature, but much, much more humid, right? Now I'm much more comfortable, right? People say, oh, it's a dry heat or it's a wet heat, right? So that wet heat, where it's more humid, is less comfortable to me because my body cannot sweat it away as easily. In fact, in Vegas, I don't even see it on my skin, right? But in Miami, not only is it on my skin, it's rolling down my leg and it feels disgusting, all right? Sorry for the folks that are from Miami, just giving an example here. So the amount of humidity around your body dictates how fast you can reject heat from your body to the air around you via evaporation. The drier it is, the faster I can give the heat up. The more humid it is, the harder it is to give the heat up. So in the summertime, when I'm fairly warm as it is and I'm trying to get rid of heat more rapidly, I would prefer a drier air around my body, and that would be more comfortable to me. If it's the heating season and my body's trying to save some of the heat and I don't want to give it up as quickly, I prefer to be in a humid environment or a more humid environment so I don't give the moisture up as quickly. I don't give the moisture-based heat up as quickly. That's why I typically in spaces will add a humidifier and use that in the wintertime, and will dehumidify in the summertime. Bruce wrote a question, static electricity from low humidity. Yes, the humidity content in the air has an effect on lots of different things. Different viruses and bacteria thrive when it's dry and moist, and wood products don't do so well when it's too dry either. And one of those other things is static electricity. The drier air tends to transfer static electricity easier, so you might get shocks from doorknobs and things like that in a drier environment, whereas in a moisture environment, you won't have that effect. Ideally, our humidity target is typically on the low end, like 20-30%. On the high end, it's 60%. ASHRAE standard 55, which is the ASHRAE standard for human thermal comfort, does dictate specifically a maximum indoor humidity of 60%. It used to have a minimum of 30% in the standard. That was removed from the standard, I think, in 2004. There is no minimum listed anymore, but the old minimum was basically 30%. So that's still a target range. I'm not sure why they removed it from the standard. I think places were tending to get over humidified and causing other IAQ related problems. So that's why I think that kind of evolved out of the standard. But there is still a fixed maximum of 60%, and then the minimum, just in your head, think of it as like a 20 or 30% number. If you keep in that range, you're usually in pretty good shape. 60% maximum in many cases not only is for comfort, right, which is where ASHRAE standard 55 comes in, but it's also for controlling certain types of organisms, specifically mold. If you are at about 70% moisture for about 2 weeks or so, you're probably going to be able to grow mold. And if you're at 80% moisture, it'll probably take about 3 days to start growing mold on surfaces, right? Mold needs several different things to grow. It needs a food source, which is pretty much anything. It could be an orange on the counter, but it could be wood, drywall, whatever. It can always find a food source. You need to have the spore in the air, which is pretty much everywhere. So that's a guaranteed thing. So really controlling the moisture is your best bet. And obviously you want to control any direct sources of moisture. But then in terms of the air, if you keep things under 60%, you're in pretty good shape. So you not only be more comfortable for the human occupants, but you probably won't grow bad things in there if you can stay under 60%. So that is a fixed number that is in ASHRAE standard 55, which in some cases is code required. In some towns it's not. It just kind of depends on where you're at. But it's still a good design practice to keep it under 60. Sometimes when we do add humidity to spaces in the winter, if we add a lot of humidity, we can cause condensation on windows. Remember before when I said, the single pane window on a minus 10 degree day has an inside surface temp of 10 degrees, and the double pane was like 46 or 47 degrees. Those surface temperatures, if they are, too close to the dew point of the air, then I'm going to have condensation form on those surfaces, the windows, and that condensation is going to run down the windowsill and eventually cause damage. So typically we will reset the indoor humidity settings when we have a humidifier to track the outdoor temperature to avoid condensation on surfaces such as windows. So this is just kind of a chart of some recommended settings that you might use. If you're comfortable at 30% humidity on a 10 degree day, but drops down to minus 10, we might drop you down to 20% humidity. By the way, this was assuming double pane windows in this example. So you might do that reset type of thing to kind of prevent other things from happening. On the dehumidification side of the equation, most buildings don't have separate dehumidification equipment installed, residentially or commercially. It does happen sometimes, right? And if you got a swimming pool or a fitness center, yeah, you're probably going to have dehumidification equipment installed. But if it's your typical office building or a classroom or something like that, you're probably not. And same thing in your house, you're probably not going to have separate dehumidification, and you probably don't even need it in a lot of cases. But dehumidification does take place as a byproduct of us cooling the air during a regular cooling cycle, right? So when I first turn my air conditioner on at my house, let's say, my compressor runs, I start getting that cooling effect. The temperature of the refrigerant coming to my indoor evaporator coil is dropping, right? And it's dropping and it's cooling off my air. And at first, when I first turn my air conditioning system on, I don't see any moisture coming out the condensate line off my evaporator coil. But after it runs 5, 6, 7, 8, 9 minutes, whatever it is, I start dropping the air temperature going across that coil down below the dew point, which means it's 100% saturated and can't hold any more moisture. And that moisture condenses on the coil surface and then drains down the coil and into the pan and out the condensate drain, right? So in order for me to get dehumidification to happen as a byproduct of cooling, I have to have cooling cycles that are long enough in order for the evaporator temperature to get cool enough to get it below the dew point of the air. If that doesn't happen, I don't get any dehumidification. So the worst thing I could possibly do on an air conditioning system would be to shut off the compressor prematurely. The problem with lots of houses and buildings is that the HVAC equipment is oversized. And this class is not about oversizing. I have separate classes on that, but it's a pet peeve of mine. But in general, I'd say well over 90% of the equipment you interact with is probably a little bit oversized, if not a lot oversized. The more oversized it is, in the cooling scenario, the more oversized it is, the faster the thermostat's going to get happy, right? And that might sound like a good thing at first until you think about what I just said. If the thermostat gets happy too quick and it meets its set point, say 74 degree temperature in the room, it shuts off the compressor. If it shuts off the compressor before I've dehumidified, I'm going to have a humidification problem in the space. So what I really want is I want the thermostat to take a very long time to get happy. So I get really long cooling cycles. So I dehumidify a lot, right? So the best way for that to happen is to not oversize the equipment. We used to, in some of these classes, tell people, to downsize the equipment, but that got a little misconstrued. We didn't mean downsize it from the load. We meant downsize it from the grossly oversized thing that was there. So instead of saying downsizing, we now typically refer to it as right sizing. We want to correctly size the cooling system for the load and not have safety factors in there that cause us to have bigger and bigger equipment, because then I have poor dehumidification. In an existing facility, you can usually quickly identify, at least I can when I walk into a building, if they have oversized equipment without even looking at the equipment or doing the load calc. If I walk into a building on a fairly hot day outside, 90 degrees plus outside, and they've got the thermostat jacked down to like 69, 70, 71, something like that, I'm going to guess the equipment's probably oversized. Because if I had the right humidity in the space, I could probably make you comfortable with 75-degree air or higher even. And if I don't have that in the space, people tend to make themselves comfortable from a moisture standpoint by driving the cooling set point down on the thermostat. So really cold set points are usually indicative that people are trying to dehumidify their space, and the only way they know how is to keep jacking the set point lower and lower and lower. So correctly sizing the equipment will prevent a good portion of that. Other things we can do to more actively dehumidify the system, other than correctly sizing the equipment, which we should always do, multiple stages of equipment is very beneficial. The more stages, the better, generally speaking. If I have one stage equipment, which basically means I turn the compressor on and that's it, and I get whatever I get, that's fine when it's 92, 95 degrees outside, something like that. But when it's 78, 80, 83 degrees outside, I don't need as much cooling. So I'd like to have multiple stages so I can only put on what I need. Two-stage equipment is readily available in everything from the smallest residential to the largest commercial unit. There's no reason that 100% of the time you shouldn't be able to find a two-stage piece of equipment to do the job. Additionally, there's equipment that is even more stages available, and you can get 3, 4, 5, 6, 8, 10 stages depending on what kind of equipment we're talking about here. So the more stages, the better for dehumidification, because then I can put the exact amount of cooling on you need and get very, very long run cycles, which means I get excellent dehumidification. The other thing I could do is I can slow down airflow. So sometimes we'll initiate, if we have a thermostat that has a humidity sensor in it, we'll have what we call a dehum terminal on that stat, and that wires to the dehum terminal on the HVAC equipment. Dehum basically means that my thermostat is happy from a temperature standpoint, but he's a little bit high on the target for whatever humidity I set it for, say 60% in our example. So I'll ask for dehumidification of the HVAC equipment. What that equipment will then do is turn on the least amount of stages possible. So on a 2-stage unit, it'll turn on first stage only. On a 5-stage unit, it'll turn on first stage only. And then what I'll do is I'll slow the blower down that moves the air across the evaporator, slow down the supply fan to increase the amount of time the air is in contact with the evaporator coil, which helps me pull more moisture out of that air, right? So I can do those kind of active things to help dehumidify when I have more extreme scenarios. And then if you have spaces that have lots of humidity generation, meaning that you have a locker room with showers, or you have a workout fitness center, or you have some kind of lobby with a bunch of water fixtures and fountains and stuff in it, you're generating all this moisture. In those cases, you're going to need specialized equipment that has the ability to subcool and then reheat that air back up to a comfortable temperature, right? So like hot gas reheat or humidizer or something of that nature. Peter typed in a question, any suggestions for a residential system that is oversized? Well, the suggestion would be to replace it with a correctly sized system. I'm assuming you're looking for some kind of like magic thing, because your next question said, with slowing the blower speed, what delta T are you aiming for? So in the dehumidification mode, the delta T is not my main concern. My main concern is getting the coil down to the dew point temperature of the air so I can remove moisture from it. I'm not targeting a specific delta T on dehumidification mode. But to answer your question, whether it's residential or commercial, the biggest step to correctly dehumidifying the space is to put in correctly sized equipment that is not oversized, meaning no safety factors. And for 50 years, we've added safety factors to our load counts, we meaning an industry. So we need to kind of remove that process. All right, I'm going to stop talking about sizing because I will go on for 4 hours talking about that particular pet peeve. Let's just pull up our next quiz question here. So quiz question number 3. All right, so relative humidity tells you what? Tells you A, the exact amount of moisture in each pound of dry air, B, how close the air is to being saturated with water vapor, or C, how much more moisture the air is able to hold as a percentage, right? So this one's a little bit trickier than some of the other ones, so we'll see how folks do. Read it carefully, please. Relative humidity tells you A, the exact amount of moisture in the air, B, how close the air is to being saturated, or C, how much moisture the air is able to hold. While you guys are doing that, I'm going to go back to Peter's question a little bit more when he asked with slowing the blower speed, what delta T are you aiming for? And I mentioned it wasn't really a delta T, target, but just from a general airflow standpoint, historically, systems have been designed to use 400 CFM per ton. Somebody picked that number back in 1950 or whatever. We've been riding that number ever since. Residentially, a lot of systems we ship at Carrier, at TEC, are already defaulted to 300 CFM per ton. Over the years, we've dropped that number down. If you're in some really dry climate like New Mexico or Arizona or something, you need a lot of airflow. But in places that are more temperate climates and more humid climates, I want the blower speed to be lower so I get more latent transfer. If I slow the blower down, I get more latent capacity versus sensible capacity. So a good target is about 300 CFM per ton if the equipment you have is designed for that. In an existing system, it may be not possible to slow it down that much if you can't get air to the furthest duct run, right? So if the system was designed for 400 CFM per ton and you drop it to 300, you might be great and it might do a great job. However, you might have situations where you can't get air to the furthest zone. So like in a residence, that's going to be the bedroom at the end of the long ranch house or the bedroom above the bonus room garage type thing. So you got to make sure you can still get the required airflow out those places. But if you can, start dropping that CFM down. 400 CFM per ton of cooling would be the maximum that you probably would have for a normal comfort application in the Chicagoland area. But you can drop that down to 350, 325, 300. Some cases you could drop it down to 275, although you might have some situations where you could have refrigeration problems, but you can do it in some units. But 300 CFM per ton is probably the new standard, if you will. Anyways, I'm going to close the poll here, the question. Talked a little bit long there. And share the results with you. 69% of you got it correct. Relative humidity tells you how close the air is to being saturated with water vapor. Several folks did pick C. C is the opposite of what it is, right? So how much moisture is it able to hold as a percent? How much more moisture? It's not how much more moisture it's able to hold. It's how much moisture it's currently holding, right? So it's not more. That more word is kind of the key that threw some of you guys off, I think. All right, so let's talk about what we can do with some of these things. So we got the convection, radiation, evaporation, and conduction, and I previously talked about those as if they were all independent things, just to kind of explain them. But in reality, all four of those things are pretty much going on all of the time, right? So they're all working together. And if I have deficiencies in one area, I can make it up in the other area, right? Like I said before, if I'm really hot and I don't have air conditioning to change the temperature, I can stand in front of a box fan and become somewhat cooler. So I can make things up. What I'd like to do is have all these things being controlled at the same time by me with the HVAC equipment and doing it in such a fashion that nobody really knows that I'm there doing it, right? So I got those four types of heat transfer and things that I'm going to control in the space. I'm going to control the air temperature for sure. That's my thermostat. He's dictating that. If there's one thing that's going to be right in the space, it's going to be the air temperature. Although it may only be right at the thermostat, right? And 300 feet away at the other end of the building, it may not be right. But at the thermostat, it's going to be perfect. I can't control the relative humidity. A lot of systems don't actively do that, but it's pretty easy to do that with lots of systems. And you should start thinking about ways to control the humidity to some degree. Like I said, by forcing cooling on and slowing down the blower and stuff like that. I can control the air motion for sure. A lot of that comes into play on where I choose to put diffusers, what velocity I've selected the diffusers for. Do I have a supply diffuser right next to a return grill, or if I've done a good job of separating them so it pushes the air through the whole room as opposed to just short cycling it right back into his neighbor, right? So the things I can do to control that. The surface temperature is a little harder to control. For the most part, I'm controlling the temperature of your desk surface by controlling the air temperature, which is indirectly. In some cases, though, I can do a really good job of controlling surface temperature, and typically that's with radiant floor systems where I bury PEX tubing in the floor itself, and I run warm water through that, or cool water to temper that floor surface to kind of make you more comfortable in that regard. So we can do some stuff with that, but that's not the main one typically. Like we mentioned, clothing level does affect your comfort. Typically in the summertime, people wear less clothing. In the wintertime, they wear more clothing, which changes what levels of comfort they have. I do realize that half of you guys have kids that went to school today wearing shorts and a tank top, right? And that's not really appropriate for a 65-degree day, but they do it anyway. right? But in general, for the most part, people wear clothing that's appropriate for their activity and the time of year. So we can't make everybody happy all the time. Yeah, if I have a house and one guy lives there, I should be able to make him happy, assuming he knows what he wants, if he even knows what he wants. But as soon as I go to a building that has multiple occupants, like a commercial building, there's no way that I'm going to make 100 people happy. So kind of our goal is to make 80% of the people happy. That's generally considered to be acceptable. You can't make everybody happy. It's just not possible unless everybody had their own building with their own HVAC system and everybody was, doing their own thing. But as soon as you start sharing office space and stuff like that, or sharing a classroom, everybody can't be happy. The things that are going to determine the happiness of these people, like we mentioned before, clothing level. You can't control it, but they're going to change clothes, and one kid's going to be sitting at the desk in shorts, and the next one's going to have a sweatshirt on. It's just the way it is. Activity level, you can't control the activity level, but they should be able to tell you what the space is going to be used for, right? Is this going to be an office? Is it going to be a fitness center? Like, what are you doing in this space? So that one's you should be able to design for. Temperature, we talked about humidity, air motion, surface temps. Localized conditions, people have different expectations in different climates for what comfort is. So where you're at in the world does sometimes make a difference. Like we said, clothing is an insulator. It actually does have an insulation value. It's called a CLO, clothing insulation value. Once again, a 3-letter acronym. We're really creative in the HVAC world here. Your typical suit, if you will, which is what the original system was based on years ago, is a clothing value of 1. And the more or less layers you have from there, it changes it. So if you were to wear your suit, but you also had a sweater on under your suit jacket, right, you'd bump up to like a 1.2 clothing level. If you were sitting here at your desk in, khakis and a polo shirt, you're probably like at a 0.6, 0.7, 0.75, something like that. So there's these charts that determine the clothing values and the insulation value. We don't spend a lot of it. We all know that it exists and we think about it, but we don't spend a lot of time on it on the HVAC side because, like I said, we can't control what you wear. We also can't control your activity level, but it is important to note that your activity level determines how much heat you generate, and what you're doing has a different effect on your metabolic rate. And the metabolic rate is a heat measurement, right? It's actually measured in one metabolic unit is 18.4 BTUs per hour per square foot. So if I'm sleeping, my body's barely doing anything, so I'm not generating hardly any heat at all relative to when I'm doing something active, like sitting in a classroom or at a desk, or on the far right, if I'm sprinting on the treadmill at the gym, my metabolic rate and hence my heat generation goes up. It's like 3.5 times as much between sleeping and running on a treadmill. So I need to know what the space is going to be used for in order to be able to correctly calculate the predicted heat load from the building occupants. Eli points out an interesting fact that elderly people have their bodies have changed, right? And they have different, as Eli puts it, different subcontinuous layer of fat. But as you all probably know, older people tend to have poor circulation as well, and their body doesn't generate heat as much as younger or more active people typically. So point being, if you're designing a senior home or something like that, you're going to have different targets as well. People are not going to be comfortable at 72, 73, 74 degrees. They're going to expect something in the high 70s probably for those kind of environments. So sometimes your age does have an effect on it. The really, really young infants and the really, really elderly people are going to have different needs from the average person being age 3 through 70, if you will. So our effective temperature is not just the actual temperature, but it's the temperature with the humidity involved, right? Your humidity affects how you perceive comfort. So in the wintertime, what you're probably going to want to do in many cases is add moisture to some of these spaces in order to give that better comfort feel. In the summertime, you're going to want to remove moisture to give you a better perception of how you feel. So to illustrate that, we go back to our psychometric chart, and this is a zoomed in picture of our psychometric chart, right? So moisture is on the vertical axis, temperature is on the horizontal axis. And these two boxes here, if you graph out on ASHRAE Standard 55, all the different parameters, and by the way, there's a software tool to do this that ASHRAE has called the Graphical Compliance Method for Standard 55. If you can't find it, let me know and we'll get it to you. But you can graph it out. And basically here what we have is we have it plotted out based on the clothing level, the wintertime in gray, and in the summertime is in white on here, on what temperatures and moisture contents you would expect. So for example, if it was 70 degrees in the space and 50% humidity, that would be totally fine in the wintertime. In the summertime, that's probably going to be too cool. I'm going to have something a little bit higher to make people comfortable, right? So maybe it's 75 and 50%, right? Or maybe instead of that, it would be a cooler temperature, right, and a lower relative humidity. So I got these two very skinny slivers of the whole Psych Chart that people are actually going to be comfortable in, and a very skinny sliver between winter and summer even overlaps, which is why a lot of your comfort complaints come in the spring and fall. Not only is your equipment inappropriately sized for those seasons, but the chance of getting it correct for somebody is pretty low. We do have some absolute limits. We never want to be above 60%. We talked about that previously. That's dictated by ASHRAE standards as well as potential for mold growth. So I don't want to be above 60%. I totally want to avoid that. There's no lower limit minimum, but I tend to want to be above 20, 30%-ish. So the box gets really, really small on where I'm trying to be with all this stuff. You shouldn't have summertime set points that are cooler than the wintertime set points on your thermostat. I go to facilities, people ask for that. Almost all cases it ends up getting traced back to oversized cooling equipment that's driving people to want set points below 75 degrees in the summertime. You can go back to my regular mouse here. Oops. In a lot of cases, energy codes might dictate set points. It's pretty common to have a 5-degree spread between those. International Energy Conservation Code, at least when you look at the residential portion of it, it actually dictates that you have to design for 70 degrees heating and 75 for cooling. That's actually written into the code. If you're in Illinois, like most of you are, we have an amendment to that, and you are required to use 72 and 75 instead of the international 70 and 75. But the point being is that the codes have realized that the closer the set points are, the more energy you waste, and you should have some spread between those two. If you're comfortable at 73 degrees in one season, you're probably going to be comfortable at 73 degrees in the next season. And you can't tell me that all of a sudden 74, 75 is going to be that much more horrible. But it's very predictable. You can plot this stuff out, and there's a software tool to do that if you're interested. There are other factors, though. It's not just temperature and humidity, like we said before. Air motion can make a big difference. And like we said, if you're hot, having more air motion is going to be beneficial to you. If you're already cold, you want less air motion typically. So it says here that we can have the temperature be compensated by up to a 7-degree effect by having good air motion. All of you guys have probably put a ceiling fan in a bedroom or something like that, and you know that you can lower your thermostat when you sleep by using your ceiling fan. Or maybe you did an industrial facility and you put in one of those big ass fans. That's literally what the name of the company is, big ass fans. These huge turnover fans they put on the ceiling to have low velocity air be generated and move throughout the space a little better. That kind of stuff can improve the temperature comfort without actually changing the temperature. The other thing is in the ASHRAE standard 55, there are limits on the temperature delta you can have between the floor, which is considered 6 inches above the ground, and the top of the occupied space, which is either 3.5 feet for a seated space or I believe 6 feet for a standing space. And above that, you can do whatever you want. We don't care if it's 100 degrees above the 6 foot mark. That's fine. Of course, if you're 6'6", you're probably not happy, but for me, it's fine. Generally speaking, any more than a 5-degree difference between your feet and your head, people perceive that and they're going to complain about it, and it's not going to be comfortable, regardless of the actual temperatures in the room. So 5 degrees sounds like it's really easy to hit. Oh, I set my thermostat for whatever, 70 degrees and 72 degrees in the wintertime, and everybody's happy, right? Well, it's 72 degrees at the thermostat, but what's the temperature at the floor? So the biggest thing that happens in these cases is mostly in commercial buildings, we have overhead heating systems. That's very common, meaning we have the supply grills and registers at the ceiling level. There are some things that happen with that, both in terms of just physics as well as in terms of standards and codes. The hotter the air is coming out of the diffuser at the ceiling, the more likely that air is to stay at the ceiling, right? Because we already know that hot air is going to rise. I rely on my diffuser and the orientation and directional turning vanes on there to throw the air down into the space. Well, if the air is really hot, my diffuser can't throw it down as easily, and the air hugs the ceiling. There's actually a prescribed rule for this, but it's been in the ASHRAE handbook since the 70s. It's in ASHRAE standard 55. It's in ASHRAE standard 62.1, which is the ventilation standard. And that rule is for overhead heating systems, you can have a discharge air temperature coming out of the diffuser of no more than 15 degrees above whatever the space temperature is. Otherwise, you're not going to get proper mixing in the space. And the purpose of the diffuser is to get mixed air. That's what his job in life is. So if you have a 70-degree space, the maximum heating discharge air temperature you should ever have coming in at the ceiling level is 85 degrees. If you got a 75-degree space, then the maximum would be 90 degrees, right? So 15 degrees above the space temperature is the hottest air you could possibly put out and not have a stratified space. If you put out hotter air, let's say you design your system for 120-degree supply air, which is actually a very common design point. By very common, I mean almost all the jobs that I go to. But you put it out for that type of air, what happens is that hot air will hang at the ceiling, and it'll float along the ceiling, and it'll go back out the return grill. And the only way I heat the space is by heating the ceiling, and then that air heats the layer of air below it, and the one below it, and one below it, until basically I get my 70-degree set point at my thermostat. My thermostat's 70 degrees, right, in that scenario. My ceiling is basically 120 or 115 or whatever, and my floor is 52, right? What's the thermostat say? The thermostat says life is great. I'm 70. That's what you asked for. I did exactly what you wanted. But yeah, my feet are 52 degrees and I'm freezing, right? And then everybody puts electric space heaters under their desk, and you guys know that whole drill or whatever happens there. So it's a really big deal about not having more than 15 degrees above the space temperature for overhead heating systems. That's the absolute maximum. If you have more than a 15-degree delta T between space temperature and discharge air, and you're following ASHRAE 62.1 as your ventilation standard and code, you're required by code to bring in 25% more outdoor air ventilation air, right? You basically get effectiveness multiplier added to your formulas of a 1.2, which means you have a 25% penalty of air. So if the table told you, if you looked at the tables for people in square footage, and it said you had to bring in 1,000 CFM of outside air, but you designed your system for warmer than 15-degree discharge air above the space, then you have to bring in 1,200 CFM of fresh air instead of 1,000, because they recognize that when the air is really hot, it short cycles and goes right back out the return. That's a pretty big deal on the heating side if you can avoid that. Obviously, the better thing to do would be to heat from the floor, right, and return from the ceiling. But for cooling, it's better to cool from the ceiling and return at the floor. And nobody's going to put in a double duct system, one for wintertime and one for summertime. So they pretty much go with the dominant mode, which for most commercial buildings is cooling mode. Plus, a lot of the equipment is rooftop based, and it's shorter duct runs and easier to put ducting in a ceiling plenum than it is under the floor. So you tend to have a lot of overhead systems in a lot of commercial buildings. Just keep that delta T in check for the discharge air. From a perception standpoint, people typically can't detect, almost nobody can detect a 1 degree temperature difference. It's very rare if someone can, if you change the room temperature from 72 to 71 and someone actually knows that. Most people can't perceive that 1 degree difference. And usually most people can't perceive, 2, 3, 4 degrees either. So I can have a little bit of swing involved in there in terms of comfort, but it's still got to be reasonably tight. Kind of already talked about that. So sometimes we use these charts when designing a system or setting up a system. It's kind of easy to fill out in advance beforehand, so I know what I'm targeting, and then my building owner or occupants or whoever can agree upon the stuff that we're trying to set. Right. So, for example, I mentioned for heating and cooling set points. Typically, my design is 70 for heating, 75 for cooling. I know that in some people's designs, they've been dropping that 75 number cooler and cooler, and people, I want my building to get down to, you got to make me 69-degree air. I'm a fat guy, I got to be cool in my office. You get those comments all the time. That oftentimes initiates with people expecting it to be much colder because they have oversized equipment in their current lifestyle, and they need that colder temperature to get the humidity down. Right? If you're able to keep the humidity in check by correctly sizing the equipment, you probably don't need those super, super cold temperatures. In some cases, like in the state of Illinois residentially, you have to design for 75 cooling. You're not allowed to design for something lower. And if you have a good inspector in your town, he's going to flag that and make you redo the load calcs with a 75-degree temperature. Likewise, on the heating side, depending on your code, it's going to be 70 or 72 degrees there. Unoccupied time is interesting. I don't need to size the equipment for the unoccupied time typically because it's going to be relaxed set points from when the occupants are there. But it's kind of nice to have on my design sheets what I want from the get-go. So this is showing 85 and 60. Me personally, I default to 80 and 65, meaning that in the summertime, your set point is 75, and I bump you back to 80 at nighttime. And in the wintertime, your set point is 70, and I bump you back to 65 at nighttime, basically 5-degree setback, if you will. Traditionally, the bigger the setback, the better the energy savings has been, right? Most equipment that you had in a lot of existing systems was one-stage equipment, or even to lesser degrees, sometimes you'd have two-stage equipment. And when I turned that equipment on the next morning, I pretty much turned it on, let it go balls out, try to satisfy the set point, everybody's happy. And the bigger the setback I had at nighttime when no one was there, the more energy savings I would have. Because remember I said that the heat transfer rate through the wall is a function of the delta T through the wall. The bigger the temperature difference, the faster the heat transfers. So if it's a 0-degree day outside and 70 inside, it's a 70-degree delta T. Heat moves from my inside to outside at a certain rate. If I lower your set point from 70 down to 60, now it's only a 60-degree delta T. So the heat moves at a much slower rate out of my building. So generally, if I go into setback mode and my temperatures inside are a little bit closer to my temperatures outside, then I don't lose heat as fast. Now, I say that's the old school way because sometimes what's been happening with newer equipment, especially residentially, equipment controls have gotten much smarter, and they realize that you've got lots of stages in some of these units, 5 stages, 60 stages, whatever it is, modulating gas valves, stuff like that. And they take into account the fact that most pieces of mechanical equipment are the least efficient when they're operating at full load operation. They do much better at part load. For example, in a gas furnace, I might have a certain size heat exchanger, my flame is at a certain rate, and I got a certain efficiency. If I was to double the size of that heat exchanger, that extra surface area would give me more heat transfer and hence higher efficiency levels. Well, I'm not going to double the heat exchanger during operating time, right? I can't just randomly do that. But when I don't need full load, I could throttle the burner capacity back and give you less gas flow, which is kind of the same effect as having an oversized heat exchanger during those part load scenarios. So I'm able to be much more efficient than whatever the published data is for a piece of equipment when I operate it at part load. Same thing happens on the cooling side with the surface area of the evaporator and condenser. If I can throttle back the refrigeration capacity but keep the same size surface area of my coils, I tend to be more efficient. So what I want to do, if I can design it into my control sequence, is I want to avoid high fire whenever possible. But the flip side, I want to get that less delta T from inside to outside the building during setback to get that savings. So what some of these more sophisticated controls are doing when they're integrated with the actual equipment, they're actually calculating right now what's the best setback for me to have in order for me to not have to go to high fire the next morning. What can I do not to go to high fire, basically? So you set it back for 60 degrees in setback mode for heating. It may hover you at 67, 68, and now let it go all the way back to 60 because it knows that's what it needs to do on a day like today with the current weather conditions to not have to go to high fire tomorrow morning and get you the most savings possible. Right? But in general, for most equipment, single and two-stage equipment, you want to set it back as aggressively as you can as long as you still have time the next morning to heat up all the surface temperatures before people bitch in the morning, before they complain, excuse me. Humidity, typically we're designing for 50% humidity, and we might put controls in there to physically cap it at 60% maximum and then do that dehum thing I was talking about earlier if it gets above that. In the wintertime, there's typically no lower limit established, at least by standards and codes, but you probably want to look for like a 20 or 30% minimum. Air motion in the actual space, 15 to 30 feet per minute is a pretty normal range. If you get higher than that, people complain about it being drafty. If you get lower than that, they complain about it being stuffy. By the way, this is air motion in the space, not air motion in your HVAC ducts. In your duct system, you're going to be looking at, 400 or 500 feet per minute, something like that. Ventilation rate is dictated by code. This was based on the old standard on a lot of the existing buildings we're going to, which is 20 CFM per person in an office building. The new current standards from 2004 and later for an office building would be 5 CFM per person plus 0.06 CFM per square foot. And you would add those together to get your total airflow required for ventilation air from outside. There's different standard levels for different types of spaces. That was an office example. Residential is different, fitness center different, daycare different, school different, etc. But just you got to go to the appropriate document for your building type and look and see what the ventilation rate needs to be. You do want to decide what kind of filtration you're going to use at the early end of the project. This shows a MERV 6 pleated filter, which is kind of like the bare minimum. If you want better filtration, you want to take that into account in advance because it will change in some cases fan sizes and speed and stuff like that. So those are some kind of notes you can look at to see what typical designs might be. This is an office building example. There's a manufacturing example. The set points get spread out a little bit because we don't have as big a concern in there. But depends on what you're manufacturing. If you're making circuit boards, then that's going to be different, right? All right, let's do another quiz question. So question number 4. Which combination will make a person feel warmest? So choice A is decrease the temperature, increase the humidity, decrease air motion. B, increase temp, increase humidity, increase air motion. C, increase temp, decrease humidity, decrease air motion. And D, increase temp, increase humidity, decrease air motion. So it's a little bit of a long worded one there, if you will. But just try to think it through and which would be make you more comfortable. Increasing temp or decreasing temp, increasing humidity, decreasing humidity, increasing air motion or decreasing air motion. Which will make you feel warmer? Most of you guys are doing pretty good with the correct answer here so far. We only got 68% of people answered so far, so I'm going to give it another 15 seconds. And if you need PDHs, make sure you answer the questions, please. I cannot change them after the fact. All right, I'm closing that down. And 84% of you got the correct answer. If I want to feel warmer in a space, I can increase the temperature, which pretty much eliminates answer number 1, right? Increase the humidity, right? So now I'm choosing between B and D, and then decrease the air motion, right? So D is the correct answer. Increase temp and humidity and decrease the air motion will make me feel warmest. We're also going to go ahead and do question number 5 right now as well. So let's populate that. What is the maximum allowable relative humidity per ASHRAE standard 55 and good design practice? So what's the absolute maximum that the standard is going to allow you to have for relative humidity in a space? Choices are 50, 55, 60, or 65% humidity. Most of you guys, actually everybody got this right so far. I probably actually mentioned it in 2 different sections today, so hopefully everybody remembered from that. Daniel asked an interesting question. We'll read that while you guys are answering the other one. How do you determine air motion in the space? And he asks combined diffuser CFM divided by space volume. So the way I don't design diffusers personally, but the few times that I have been involved in that, what I normally do is I go to the diffuser manufacturer's catalog, which is typically Titus or Kruger or one of those guys, and in the catalog they'll actually have the throw data of the different scenarios, and they'll give you data in the catalog for typically 50, 100, and 150 feet throw. And what you're normally trying to do, like say in a perimeter zone, remember I mentioned you had to be no more than 15 degrees above the space temperature? There's other rules that kick into ASHRAE 62 as well that you need to follow in order not to have to do the penalty on outside air. Another one of those rules are that using the 150-foot throw data from the manufacturer's catalog, you have to throw the air out the diffuser to the glass side of the perimeter and to the interior side, and throwing it to the glass side has to make it halfway down the window. So that typically determines your diffuser selection and placement. And if you follow those kind of rules, then the actual air motion by the occupants will usually be pretty good in that 20 to 30 feet per minute range. Obviously, some of this has to do with where the person's sitting. If they're sitting underneath the diffuser, it's going to be too much velocity, right? So I want 15, 20, 25, 30 feet per minute maximum where the person is sitting, which is not directly related to what my diffuser is doing in my HVAC design per se. Sometimes you can't avoid it, but people should not be sitting under diffusers or they're always going to be unhappy. Don't put your desk by the glass window kind of thing, because we're trying to throw air down the glass window to keep the glass tempered. So you can't sit by the window, which is obviously something people like to do. So it's hard to determine what's going to happen in the space itself by the occupants. But if you follow the rules we have for determining what throw we want out of the diffuser and how far we want to throw it down the wall, you're usually in good shape in the actual place where the person is actually sitting. All right, let me close this question here. So the answer was C. 60% relative humidity is our maximum. All right. What just happened to my screen? My screen just went to some weird sleep mode. That's okay, because we're actually at the end point of part 1 of this webinar. So my screen must just magically know that I'm at my end point somehow. Next Monday will be part 2, and there'll be another hour and a half on next Monday, and there'll be another 5 quiz questions that you'll need to answer if you're trying to get PDH credits. When we start off on Monday, we're going to kick off with talking about different types of equipment side of things. So we'll talk about furnaces, we'll talk about heat exchangers, we'll talk about the refrigeration cycle. So we're going to try to tie in some of these principles we just talked about in terms of how people are comfortable and how heat transfers, and tie it into the actual equipment and how we're going to design and lay that out in order to make people get the cooling and heating and humidification effects that we've been talking about. So that's it for today. I will see you guys on next Monday, same time, noon. If you have any questions that come up in the meantime, please let me know, and I will do my best to answer them. And I will put my contact info back on the screen for you right now. Maybe. Maybe not. Maybe I won't, because I'm not smart enough to know how to do that. Oh, I had the poll question up, that's why. All right, now it should be that information. All right, thank you guys very much for your time. We'll see you Monday.